In the last video clip we saw how difficult it is to control a tilt rotor. But this combination of a fixed wing airplane and a helicopter is very tempting, and there are other examples. For instance, the British Aerospace Sea Harrier combines the features of a helicopter and a jet, and you can see here this is one of the exhausts of the jet engine. So it doesn't have an exhaust on the back of the plane, but there are 4 of these exhausts located at different positions around the aircraft which lift the aircraft, and there's a small vent at the tip for control. This Sea Harrier was very successful, used for short takeoff and vertical landing, STOVL as it is called, in marine operations by the British. And it was also copied by the Americans and built under license by McDonnell Douglas, and this type is called the AV8, and it's basically the same principle as the Harrier. And of course nowadays you have relatively new aircraft which also tries to combine the jet and the helicopter advantages, and that is the Joint Strike Fighter, or F-35 Lightning, which uses in essence the same principle as the Harrier but has a slightly different mechanization. And here we see a cutaway drawing of the Joint Strike Fighter, and instead of 4 exhaust pipes around the fuselage, we see that the normal exhaust points to the back for normal flight, but can be rotated downwards for vertical mode, and together with an extra fan in front of the aircraft and 2 exhausts in the wing, you can balance this aircraft. And controlling the Harrier was sometimes called balancing on a pole, because it was very unstable, and beyond a certain bank angle in hovering mode you were unable to control the aircraft. With the Joint Strike Fighter the autopilot it has been improved, but still there are limits to the stability in this hovering mode, and it remains a risky operation. I also said that with the principles to fly, so being lighter than air and pushing air down, that there's a third principle, but that normally is not used on airplanes. Well, there's an exception. Rockets are sometimes used for aircraft. We see here in the background the Hercules of the Blue Angels that demonstrates the JATO rockets. And JATO rockets stands for a jet-assisted takeoff. And this JATO rockets are used to reduce the required runway length for large aircraft in wartime operations when there's only a short field available. And there are other ways in which you can use a rocket to fly. For instance, a fantasy often seen in movies is the jetpack, attaching a jet engine to your back and then taking off. And these things do really exist. They have been demonstrated, and there's currently a demonstration thing. You can fly with the jetpack, one that uses water, or one that's really a jetpack, has a real jet. And we see here a few pictures. But the jetpack looks different from what you will normally see in comics or in video games. And that is because there's an inherent stability problem with the jetpack. And let's have a look at the equilibrium of moments of a jetpack. Imagine we have a jetpack and we have somebody attached to it. Well, this jetpack will be quite heavy, so the center of gravity of the total configuration will be probably somewhere here, which means that's where the gravity pulls. Now, often you see it depicted as if the exhaust pipe, the jet, would be mounted like this, and there would be a force, a lifting force created by this jet there. Well, if we want the forces to be in equilibrium and also the moment to have an equilibrium, this means we have to lean slightly backwards to make sure that our center of gravity is above the position where we have the lift force. So here we have the lift force, and here we have the weight. However, even if we have them fully aligned, there's a problem, a stability problem, because imagine what would happen as soon as we have a slight deviation of the position, then the weight would be pulling there, and the lift would be pulling there. And this means that we have a moment which would worsen the situation. It would start rotating, so every minor deviation would result in a loss of control, a lack of stability. And this means that if we want to have a working jetpack, that the exhaust pipe, as you will could also see in the examples, is often mounted at the top. And there, for instance, like here, if we have the lift force created above the center of gravity, then we avoid these stability problems. Basically, the system looks then like this. Lift, if there's a deviation, and we can see that this will be automatically corrected, and there it's inherently stable. And then we have to lean forward, better for the fuel as well. So you will see that in jetpacks, you will always see that the exhaust pipe is mounted high, and that's for this reason. But even then, there's only a limited amount of pitch angle which you can correct, so it's still very dangerous. So don't try this at home, I would say. We are used to planes with pilots, but another type of vehicles is the unmanned aerial vehicles, or some say you shouldn't say unmanned, so uninhabited, or sometimes it's called remotely piloted air aviation systems, so RPAs. But I would like to use the normal term UAVs, unmanned aerial vehicles, which could do many tasks for which in the past we needed a manned aircraft. It's still controlled, but a manned aircraft. One of the advantages of a UAV was originally the idea to have many vehicles controlled by one pilot on the ground, one remote controller. And in this way, with using more automation, you could fly much more efficiently by having this man on the ground, controlling these multiple vehicles. In reality, you often see now with military operations, you see 4 men manning a station to control one UAV. It's getting better nowadays, but originally you needed 4 men, so this goal wasn't really met. And now you could be really happy if you have 1 or 2 per UAV. And even then, the crash rate of UAVs is still higher. And of course, we want to improve the automation. It's new that we try to control it largely automated, but it still has a higher crash rate than manned vehicles. So we're not there yet. And some people see these UAVs as well. We already had remotely controlled toy aircraft, so it's basically a toy. And you should not be mistaken in the size of these UAVs. Here we see, for instance, the Global Hawk, and that is, well, you can see the vehicle and the man in front of it. The span of this vehicle is identical to that of the Boeing 737, a large passenger aircraft. So these are huge vehicles, and which also means that there may not be a risk for pilots in this vehicle, but of course the third-party risk of the people on the ground is still quite high, and you see a lot of limitations for UAV operations in civil airspace still. Some dream of using this unmanned aerial vehicle as fighter aircraft, the unmanned combat aerial vehicle. And this is a prototype. It's not yet operational, but there are use advantages, of course. The fact that you can now pull higher G turns, so steeper turns, and you make more use of the agility of the aircraft because you don't have the limitations, physiological limitations of a pilot anymore. And obviously, for military operations, there's less risks for the pilot, and also strategically less risks of having hostages or prisoners of war. So there are huge advantages, and this is one of the vehicles that's being seen as an alternative, and some say that the manned jet fighter has already had its time and that we are now entering the age of the unmanned combat aerial vehicle. But also for civil operations, it is considered to reduce the number of pilots in the cockpit. We originally, remember how we explained, we originally had 4 persons in the cockpit, a navigator, flight engineer and 2 pilots. The navigator has been gone and the flight engineer is also gone in modern cockpits. Now we have 2 pilots and maybe we'll have 1 pilot in the near future and perhaps even have 0 pilots beyond that. There are still some issues. We want, of course, the crash rate not to be higher with unmanned vehicles than with manned vehicles, so the reliability needs to improve. And, of course, it would be great if we then can also have the advantage of having multiple aircraft controlled by 1 pilot. Civil operations are easier compared to military operations, less riskier and easier to automate as well. But there's also an extra problem with civil aviations. For cargo, it might be sooner applicable than for passengers, because the acceptance by passengers might be an obstacle. The acceptance from people on the ground, civil airspace I already mentioned, but imagine what you would think if you are a passenger in an aircraft where there's no pilot. Many people have trouble with this idea. And you wonder why, because often you already fly using the automation. But probably the risk is that, well, a situation like this, we see the cartoon here, where out of the speaker you hear, "Ladies and gentlemen, this aircraft is completely controlled by robots, so nothing can go wrong. Nothing can go wrong. Nothing can go wrong." And this repeats indefinitely. This is of course just a joke, but there is a more serious aspect of this. And it is that the computer, in case of abnormal situations, will at some point accept that it's no longer able to save the flight. It might be very happy saying, okay, error 12, and we're unable to control it. So relying on the automation completely might be a risk, while human pilots have been known to save aircraft from situations which on paper seemed beyond saving. For instance, running out of fuel over the Atlantic Ocean. There was an Airbus which, if you look at the calculations, it could not make it to an airport on land. The pilots thought it was that close, they still wanted to try, and gliding to this island, they made it. So the fact that a human pilot is also motivated to save his own life creates trust with the passengers, and we'll have to see whether passengers can do without this mechanism. Other new ideas for passenger aircraft are to increase the speed of the aircraft enormously and create hypersonic aircraft. There have been many experimental hypersonic aircraft for military purposes, but there are also ideas to develop one for civil applications. Imagine that you could fly to Australia in like 5 hours. And the idea of leaving the atmosphere and in this way eliminating drag might have some advantages as well in terms of fuel and environment. One thing that's often overlooked, however, is that as soon as you return into the atmosphere with extremely high speeds, you create an area of very high temperatures in which the nitrogen will burn. And in this way create a lot of nitrogen oxygen. So that is one of the trouble that, well, you might not burn that much fuel when you are in orbital mode, but you create a lot of nitrogen oxygen, NOx, which is a huge pollutant. Still, it is a really challenging goal. And well, the Astrox, as it is mentioned here, is one of the vehicles who wants to be able to carry passengers to the other side of the world in 2 hours. And of course, if we are able to achieve it, that would really fill a huge demand.